Welcome. In this video, we are going to implement the convolutional GAN paper from 2016. These are the results we'll get by the end of this video. So these are unbiased samples from the generator on the Elson dataset. So these are the bedroom generated by the network at the end of this video. So let's dive into the implementation. We'll use PyTorch as usual to implement all the machine learning part on some other libraries such as NumPy on the OS to load the data and process them. So we can start by creating a class to load and process the data. Because the dataset is so large, we cannot load everything in the RAM. We need to load image per image every time we sample a new batch. And this is, I think I need to double check that, but in memory, I think the dataset is 50 gigabytes, so we cannot load everything. So we create a custom class where in the constructor we load the file names of all the images in the data path, and then we create a transform to load the data and to process them. So we will resize the data to 64 by 64 pixels. And then we will normalize the data so that they are centered at 0 on the scale between -1 and 1. Then we can create the length function that will return the length of the dataset. And then we can also create the function getItem that will get a mini batch that will return an image at that index. So basically what we need to do for that given index, we need to load the image at the we need to load the file path that is that index. So we fetch the file path and then we open it and we convert it to RGB, and finally we apply the transform to it. So once this is done, we can implement the generator. So this is a generator based on the convolutional neural networks, and we are also using batch norm normalization. And then we can just override the forward function by just feeding the noise to the network. So very easy. Then we can move on to the discriminator. Again, we will just implement the architecture described in the paper. Again, using 2D convolutional layers such as batch normalization. And we use a leaky ReLU for the discriminator, while we used ReLU for the generator. And for the generator, we use the tangent hyperbolic to constrain the produced images to be to produce the pixel of the produced images to be between -1 and 1 as our target data. And again, the forward function is very simple. We just send the X data to the network. Now we can implement a few helpers, such as the sample noise function that allow to sample data from a random normal distribution and to send them to the generator. So now we have all the pieces needed with the generator, discriminator. We can sample noise and we can also sample real data. So now we can put everything together in the training function, where we take the generator, the discriminator, an optimizer for each of them, together with a data loader to get the real data. We also get the number of epochs on K, which is a well-known parameter in training GANs. So first we iterate over the number of epochs. So the number of epochs is 5, is the number of times we'll iterate over the whole dataset. Then for each epoch we iterate over the whole dataset. And then here comes this hyperparameter K. We iterate over K. So we will train the discriminator for K steps, while we train the generator for only one step. So for the discriminator, we first sample noise. We also sample real data. So the real data are X. They are coming from the data loader, and the fake data are Z. These are okay. For now, Z is just noise. We will need to create the fake data by giving the noise to the generator, is done on line 83. So we create fake data, then we feed the fake data to the binary cross entropy loss. So we compute the fake loss, then the real loss, and then we take the average of the two loss to compute the loss for the discriminator. Divided by 2 is not very needed. You can remove the divide by 2, but this is as you prefer. It is not very important. So once we have done the gradient step update, we can move on to the generator. So we will train the generator for only one step while we do k steps for the discriminator. So we sample a mini batch of m noise samples, and then we can directly compute the loss by creating fake data and computing the binary cross entropy loss. In that case, for the generator, we do not need real data. And then we can do the gradient step for the generator. And then we are almost done. What we need to do, we need to be careful about the initialization of our networks. If we are not careful, they may be stuck in a local minima or never learn. So we need proper initialization to make sure the learning goes well. So for 2D convolutions, we will set the bias to 0, and we will initialize the weights with a Gaussian distribution with a mean of 0 on the standard deviation of 0.02. And we will use the exact same initialization for convolutional, for transpose 2D convolutional layers. And for the other layers, we will keep the basic initialization from PyTorch. So then we can move on and put all the pieces together with the main function. We'll train everything on CUDA, so on GPU. The batch size will be 128, and we can create our data loader by feeding our custom dataset class, where data is the path to the data that I've downloaded from the LSUN repository. Then I can create the discriminator, the generator. I can initialize the weights by applying the function init weights that I've created, and then I can create my optimizers. Finally, I can send everything to the training loop to train the generator on the discriminator, and after this loop, I now have a generator on the discriminator that I trained that I can use to make my plots. So the number of images is 8 to the 2, so basically we have 68 images. So I'm generating as many images with the generator. So these are unbiased samples, or not samples that are chosen. We do not choose the best one. We only take unbiased samples. Then we create an NumPy array. We create a large image that will contain all the 64 images. So I'm creating a very large image. On that image, I will, for each square of 64 by 64 pixel, I will put an image. So this is what we will do now with these 4 loops. So we iterate over each row, and then for each column, and then we iterate square by square, and for each square we add the image that has been produced. We add an image per square. And then we can do the plot, so just creating the figure, showing all images that we've created. So this very large image that contains all the images, and we can save the results. So that's it, a very a paper that yielded very good results, that is not so complicated to implement. In about 150 lines of code, it can be implemented. The main maybe the complexity comes from finding the right architecture, but this is described in the paper. So I really liked this video. It will be helpful to you. Please leave the thumbs up. It really helps with this channel to give it visibility, and also subscribe for more content like that.